Okay. Well, hello everybody. I'm going to talk about percentages today because percentage problems are, I don't know, for SAT specifically, I feel like they get a lot of interesting questions because there's only so much you can do with the concept of percents, and so they they definitely obscure a lot of simple and straightforward concepts with the way they word the problem. So what I'm going to do today. And I don't normally make these separate videos, but because it actually is so straightforward, if you know how to break these problems down, I couldn't help myself, and I enjoy being able to speak again after my jaw surgery. So, uh, what I'll talk about first is in my lovely Microsoft Paint. We'll first talk about the definition of what it even means to be a percent, right? Percent, if we don't know what percent is, or even how to define that, it'll naturally be way more frustrating to solve percent questions. So we'll talk about what the definition of percent even is. And what that will help us do is that'll lead to two naturally occurring um, things that skills we'll need. We'll need to know how to convert a percentage. So convert percent into, I'll use words here. So to fractions and decimals. And decimals is always going to be easier. So I'll put that first. So decimal and or fractions. What we'll find is the definition of percent actually is itself a fraction. So we'll always have a basis to go from a percent to a fraction. That's very nice. And then naturally, if we can take a percent to a decimal or a fraction, and it's the same exact thing, it just looks different, right? Then we can go the other way, right? So we can take either something that starts as a decimal or a fraction and make it look like a, percent. So it's a decimals into percents. Both of those, I like to consider these the computational skills to have. Once you have these computational skills, it is very, very easy and much more enjoyable to then go into the more conceptual type problems. So this isn't comprehensive to everything percentages, but on the SAT math specifically, there are certain phrases that you're going to see a ton. And maybe you won't see the phrase exactly worded as such, but when you really think about it, the concept is going to be exactly the same. So there's the typical and standard problem type of X percent of Y. Okay, it'll be some question where at some point you're going to need to know how to take a percentage of just a sum number. Okay, so that's the easiest one for most people to understand. And then you get into these other two types. You get the you have some number, so it's just called X, increased by Y percent. Okay, so now this is going to be problem types where it's going to explain how you have some sort of a value and that it was increased by a certain percentage, right? So this could be like sales tax problems, or things where it's going to be like, yeah, he paid this, but there was a surcharge, or he was at a parking lot and paid this much, and there was some sort of convenience fee for the ATM that increased it by 2% or something like that. Okay, so this increased by some percent is a very common type of thing that you're going to need to know. And in a similar vein to it is the other direction, right? So if you can increase by a percent, you can decrease by a percent. So then if you take that number, what happens about decreased by 5%? Okay, so this could be problem types, word problems, coupons. Bob went to the store. He bought a sandwich. He had a coupon. It decreased the cost by 15%. Okay, so what do we mean by decreasing something by a percentage? How is that similar? How is that different from increasing by that percentage? That's kind of those two problems are so similar. Although they are kind of different, they're really not. If we understand what they're really asking of us. And then the other type of wording I want to address in this video, at least for SAT, uh, is this whole um I want some value that's some percentage, so X percent greater than uh and actually to save space I'll do this because it really goes both ways. Greater or less than some number. So you might be thinking, okay, that sounds really similar to this third kind of thing. Excuse me. And you'd be right. And they're very similar types of problems, and ultimately all of these percent problems are all just percents. But I do separate it out because the way you would set that up in the context, you'll see it slightly different, and you don't want to overcomplicate this for yourself. So this is pretty much it. If you can understand everything here on this whiteboard after we talk about it, you will more or less be set for SAT percent related problems. Again, they won't come exactly, clean cut, um, perfectly worded like these things in here. But if you understand the concept of it, it's going to be very, very straightforward. So let's talk about the definition of percent. Percent is simply means percent. Okay, so percent I know the audio transcript, that's a very unforgiving thing I just said. Percent literally is per cent, like in two separate words. Because cent, think about your units, like centimeters or something like that, right? Or century. We all know that this has to do with the concept of 100. So it's really we're saying per 100. Okay. Now, well, we've used that language to talk about fractions, right? So really, percent is per 100. It's this idea of taking a number and then sticking it in the numerator over 100. So if I want to talk about X percent, then what I really mean is I'm taking X per 100. So there you go. That's all there is to it. Every time you see a percentage, it's just this fraction. And you could see it as either. Some contexts, the fraction will make more sense. In other contexts, the percentage will make more sense. And even further, we know that we can convert this to a decimal, right? Now, obviously, I can't do it with just a general, but say let's do an example. So here's how we can get back and forth between these representations. 17%. Okay, so 17%. Really, what is that? Well, that's 17% means per 100. So I could say that 17% is the same exact number as 17 over 100 as a fraction. And if you think about this, percentages will always be super easy to convert into decimals because all we're doing is we're dividing by 100, right? We're just moving the decimal points over twice. So this is 0.17. Another example, say we have 89%. Okay, 89%. Well, if I want to convert this to a fraction, again, the definition does that for me automatically. It's 89 per cent, it's per 100. So 89 over 100 becomes that fraction. And then if I needed to make this a decimal or it's shown to me as a decimal, it's straightforward. I just move that decimal place over twice and I get 0.89. Okay. Um, I will show one specific type of example because sometimes you might be thinking, okay, well, not all fractions, will they always just have 100 in the denominator? And not necessarily. Say I had 25%, okay? If I had 25%, well, the definition tells me that 25% is 25 per 100, so 25 over 100. Yet I know that that's not in its simplest form, okay? So 89 over 100, that's in its simplest form. 17 over 100, you can't simplify that any further. But 25 over 100, we definitely can, because we all know, if you like still use cash these days, like quarters, this is 1/4. So it's the same thing as 1 over 4, okay? Now, 1/4, we can also represent this with the decimal 0.25. And notice that actually it's easier to convert to the decimal from the over 100 version. But it's good to know that you could see this fraction, and that fraction also goes down the chain to percent as well. So when we're converting a percentage into either a fraction or a decimal, this is kind of how we do it, right? We simply say the definition And if we can simplify it further, or it's possible to simplify in this case here, then sometimes a problem will express that fractional percentage with a more simplified version. If they're interested in the decimal amounts are easy because they're just going to look pretty much exactly the same, just shifted over with by 2 decimal points. Going the other direction is a little bit more difficult, just from the fraction perspective. So if I want to convert a decimal into a percent, that's actually super easy. So the easy one is decimals to percents. So decimal to percent, this is the easy one because all I have to do is undo moving the decimal point. For example, if I had the decimal 0.45, well, that's actually pretty straightforward because now I just move the decimal place to the right twice, and that gives me 45%. Nothing else to it. If I had something like 0.67, well, 0.67, I move that decimal point twice over to the right. That tells me I have 67%. Now, these are the most basic possible examples, but this is also useful for other types of decimals. What if I had something like 2.44? Well, 2.44 is a decimal. And just because there's now a number here doesn't change the definition. I just move that decimal point over twice, and I get 244%. Okay? Percentages can exceed 100, and that's okay. What about 1.01? Well, 1.01 is, if I move that decimal place over, that's just 101%. Okay, and there's something else I want to show you, like this. If I have something like maybe 0.875, okay, so now what do we do? Do we freak out because there's another number here? No, we don't freak out. We just still do the same exact thing. We move the decimal place over twice, and we get 87.5%. Okay, so that's all there is to it for decimals to percents. Very nice, very easy. What about fractions though? So fractions are a little bit more frustrating sometimes. Thankfully, on the SAT, they're never gonna give you a fraction that's gonna be super obnoxious to get to a percentage, especially if it's a percent type question. Now, what do I mean by that? Well, recall that the definition of percent itself is this whole idea of something over 100. Okay, this per 100 is huge. So if I can get any fraction to get the denominator of 100, I effectively have a percent. Okay, and so I can strategically multiply the numerator and the denominator by the same value to get a denominator of 100. Because if I can do that, then whatever happens to be on top is my percent. Okay, what do I mean by that? Well, let's take a look at some examples. Say you are given the fraction 46 over 100. Okay, I don't know why you would be given this fraction, but say it was made this easy for you, right? So 46 over 100, well, you'd say, well, it's already per 100. So this is 46%. It's per 100, per 100. Um, it's not always going to be handed to you that easy though. So more likely than not, you're going to get something like, I have 13/50ths. Okay, well, this is not per 100. That's per 50. Okay, that's not percent. But if I want a percentage, what do I know about the denominator that could strategically get me to 100? Well, 50 is very clearly, it's just if I take 50 and I multiply it by 2, then I'll get to 100. So then I'll get what I want. So if I strategically multiply the top and bottom by 2, this fraction is equivalent to 26 over 100. Okay, 26 per 100. Bingo, I have exactly the form I want. That's 26%. So the original fraction of 13 over 50 is the same exact thing as this 26%. Okay, here's another example of a fraction that will be easy to handle. Like, so 4/5. This is obviously not per 100. We can't call this 4%. That'd just be wrong. But we want the 100 in the denominator. So what do I do to this 5? What do I do to 5 in order to get it to 100? Well, I multiply by 20. So I'm going to multiply the top and bottom by 20 because if I do that strategically, then I'm going to get 100 in the bottom, and then whatever the numerator happens to be is my percent. So 4 times 20 is 80. 5 times 20 by design gives me my 100 in the denominator. And then boom, I have 80 over 100. I have 80 per 100, so 80%. So 4/5, the fraction, can really be expressed as 80%. Okay? So don't worry. You might be thinking to yourself, okay, but what if I get something really crazy, like 7/15? Well, 15 doesn't really play super nice with 100. There's no easy number to multiply to get there. And so thankfully, the SAT really doesn't handle these cases because they know that the point of the problem isn't to make you do all these crazy calculations to get a convenient value for 100. They just simply want to know, can you, recognize that a fraction needs a per 100 to be a percent. So they'll give you denominators like something over 4, something over 20, something over 25. These are values that are begging to be created into 100, right? Multiplied up to 100 so that you can get a percentage. So don't worry about weird cases like a denominator that's 13 or a weird denominator of like 43. Okay. That's not going to happen to you on an SAT percent question. That might have happened to you in your algebra class way back when, I don't know. But SAT math is different. It's a game. They want these solutions to be easy to get to without a calculator and all this crazy stuff. So there is that. So that's pretty much everything for conversion. And now let's start talking about these specific problem types. Okay, so X percent of Y. What does it mean to take X percent of something? X percent of Y. So what does that actually mean? Well, we've already know how to translate all of this. X percent by definition is X over 100. We know that this is a very common math word. If you don't know it by now is the time to learn it. The word of something, multiplication. Okay, so we got multiplication times y. It's just y. So when I say X percent of y, what I'm really saying is I'm just saying I want to take X over 100 times y. Sometimes it's easier to think of this as a decimal, so I'll show some examples of that. For example, if I said 17%, I've used that number already. I like that number. Let's do 11%. 11% of 6. What is 11% of 6? Well, what we would do is I know that if you're allowed to have a calculator, which it sounds like on the new SATs, they allow you to have Desmo. So I don't crazy times to it, but 0.11, right? So if I move over my decimal, so this is now the decimal form, 0.11 of is times 6. So in this case, that would happen to be just 0.66, pretty straightforward. So 0.66 is 11% of 6. But this number isn't what I'm concerned about. It's making sure you understand how to get to this specific step. If you can get to that step, that's going to allow you to do so much more, because oftentimes a variable will be involved. So maybe I'll be asked to do something like, I want 76% of, W, where W is the number of walruses who eat, gluten-free or something ridiculous. Okay. So in this case, if I'm setting up an equation, then what I know is I'm making my percentage into something easier to work with, like a decimal, for example. Usually it's a decimal. 0.76 of means time, so I'm just multiplying that by W. So this expression right here, however that might be interacting within my problem, that's how I can put that together. The variable might be the percentage itself, right? So you might actually get something kind of like, um, maybe we don't know the percentage, some P% of the cost of my sandwich S. Okay, well that's P over 100 times the cost of my sandwich S. So we get this PS over 100 would be whatever that value is. Okay. So the key is don't get stuck thinking it has to look only one way. Instead, remember this general structure. Your X% is always going to be either a easy to write decimal or it'll be in terms of some variable. So you can just like this, put it over 100. And then the of just simply means multiply. So you're multiplying it by whatever value you're supposedly taking a percent of. And if you could do that, you're set for a ton of percent type problems. Okay, so that's the easiest type. X% of Y. It's just a very general type. The next one I want to talk about, and they're very closely related. So I'll just kind of actually group them like this. So X increased by Y%. Okay, so now I'm saying I have some sort of a value and I'm increasing this by a certain percentage. Like tax is a very, very common application of this. So what does this really, really mean? Okay, well, let's step this back to a concept I kind of needed to pause on, so I'll do it right now. What is 100%? Like, obviously, those of you who like good grades in school and all of that know that 100% means you got all the possible points, right? But 100% really, if we follow our definition, is 100 per 100. It's the number one. It's okay, it's whole. So the value of 100% is basically just the number one. Taking 100% of something means simply just taking all of itself, right? So 100% of 10 is just 10 because that's all of 10. It's 1 times 10. And this is going to be really, really useful to understand when we start talking about increasing and decreasing because the natural question is, okay, if I'm increasing, what was the original amount? And the original amount, the benchmark for your original amount is the 100% mark because it's that 100% is just itself. So if I say that X increased by a certain percentage, what I'm really saying is I'm saying that X needs to be multiplied in a certain way. Okay, so to increase by a certain percent, not only do I need the original 100%, so I need its whole, but then I need to add on top of that this new Y%. Okay? And then this is what I am multiplying by my X. So X is increasing by this amount. Now, you don't often see it written like that. And so instead, think about this in terms of the decimal form, right? 1 plus Y% times my X. So this is really important. So X increased by Y%. What that's really saying is it's saying take 1, so a whole amount, take the original amount, let's increase it up by this percentage, usually represented as a decimal here. And then we multiply this new thing by X. And then that increased value is the increased number. So here's some examples. If I want to take the number 12 and increase it, so 12 increased, let's increase this by 50%. Okay, and the reason I'm choosing 50% is because this is intuitive. We can check this mentally. What is 50% of 12? Well, 50% of 12 is just 6. And so if I'm increasing by 6, then I should end up with 18. Okay. But if we think about in terms of this, what I'm doing is I'm taking 1 plus 50% multiplied by my 12, right? Okay, well, 50% as a decimal, that's just 1 plus, I got ahead of myself there, 0.5, right? So that's 50% as a decimal. And so what you're really computing in a calculator is just 1.5 times 12. Whoa, I wrote that wrong. 12. So 12 increased by 50% is the same thing as computing 1.5 times 12, which does turn out to be 18, right? Another example is, say I want to take um maybe I have some value uh C for the number of cats, okay? And the number of cats increased by 17. I keep using that number. I need to really, now I'll just use it again. 17%, okay? The number of cats increased by 17%. Okay, what does that really mean? Well, this increased by is telling me that I'm starting with one and I need to tack on this as a decimal. Okay, so 17% written as a decimal, if you remember your conversion from earlier that we did, that's just 0.17. And we're multiplying that by the number of cats. So to take the number of cats and increase it by 17%, all I'm really saying is I want to figure out what 1.17 times C is. And that's the value being described by this entire phrase. So once you get into that rhythm, this becomes really, really easy. Okay. Um, and not only that, but if you can understand the increased side of things, the decreased version of this problem is also just as easy because there's only one small difference. Instead of adding the percent, we're going to subtract it, which is pretty intuitive considering we're decreasing now. So let's do decreased by. If I have x decreased by y%. Okay, so instead of doing 1 plus my percentage, that wouldn't make any sense. I'm decreasing, so I should be subtracting that percentage. 1 minus my y%. So really what's going on is I'm taking the whole amount I had to start with 100% of it. And now I'm decreasing, right? So subtracting that percentage away from the whole. Whatever is left of me, that's what I want to multiply by my value that's changing, okay? So here's an example of that. What if I want to take 80 and the value 80 decreased by 10%, okay? And again, I choose these numbers because it's easy to find an intuitive solution. Obviously, the 10% is 8, so we're going to subtract 8, basically. But using this understanding, what I'm really asking for is I want the whole 1 minus 10%. So let's do 10% as a decimal, 0.1. So 10% of 80. So this is 80 being decreased by 10%. Let me do that again. So watch what I'm circling as I say it. 80 decreased by 10%. Okay? So that's what's going on here. And then obviously this is just the same thing as taking 0.9 of 80. Again, this becomes very helpful when you have variables involved. So which typically is actually what's going to be happening. So say I have I'm buying a sub sandwich, okay? But I have a coupon for 10%. I have like a 15% off coupon this sandwich. So what I'm doing, this cost of S decreased, right? Because I got a coupon by 15%. I got this lovely 15% coupon. So as an expression, what I'm saying is I got 1 minus, I'm decreasing by what percent? So I've taken decreasing by 15% of my original cost of that sandwich. So that's really just the same thing as 0.85 S. So the cost of this sandwich I'm anticipating is 0.85 S, which is what is meant by this wording of decreased by 15%. Okay. Now let's move into the last thing, like greater than or less than type problems. So if I have X% greater or less than a certain value. Okay. Well, fun fact, this is actually exactly the same thing as the whole increased by, because really what I'm saying is I'm just now wording it differently. I'm taking that percentage either more or less, so increasing or decreasing from a certain number. So we don't have to do anything different. We would just need to interpret this in its own individual context. So that's kind of the summary of everything. So if you had to write one whiteboard with all of the concepts on it, would be kind of it. It would be that X% is the same thing as X per 100. And that in general, if I want to convert to decimals, I am moving my decimal point two spaces either in the left or right direction, depending on whether I'm going from the percent to the fraction, or the decimal back to the percent. Then if I want to take X% of a number, all I'm asking is to make the computation of that percentage, so whether as a fraction or a decimal, multiplied by that value y. And if I want to do X increased by a certain percentage, then what I'm really doing is I want to start with the whole thing, 100% or 1, plus, because I'm increasing, my percentage, and then multiply it by what I started with. And then X decreased by a certain percentage. Well, that just means I take the original amount, I'm decreasing, subtracting that percentage, multiplied by what I had to start with. And with those formulas or expressions, you can solve pretty much everything. So what I'll do is actually now, I'll stop share. I'll switch over to some of these problems here. And then let's just take a look at, I mean, straight away, look at this language, right? Increased, increase, decrease. Let's do question 3. Magazine article, blah, blah, blah. That's a whole bunch of words. I don't really care. So here's the question. How did the average number of hours gamers spent playing games per week change from 20? So I need to compare. Where did I start and where did things end? Okay, so things started at 5.6 and they're now up to 6.3. How am I going to compare these things? Okay. Now, clearly, 6.3 is a bigger number than 5.6. So choice A just doesn't even make any sense because we're not decreasing by anything. Okay. We're increasing. Um, what we're really saying is, did 5.6 increase by 7, 11.1, or 12.5% in order to give me this new number of 6.3? Okay. So let's think back to what this wording meant. Well, to increase by a certain percent meant to take 1 plus whatever that percentage was, multiplied by my starting amount. In this case, the starting amount is in 2012, okay? So the 2012 number is 5.6. So that's the number we're interested in. This, and we happen to be told what this should come out to be, right? After making this specific increase, we should end up with 6.3. And before you know it, you have an equation. And that equation has only one unknown. And that one unknown can be isolated for and solved. So I'll walk through this one in full. But technically from here, this is just a linear equation. Since we have the percentage as an unknown, it can help to write this as a fraction. So that's one way you can do it. Because I think now on the SAT, you're allowed to use a calculator. This is an excellent position to utilize plug and chug because it's just super fast. So if you wanted to do the plug and chug version, this is what I would recommend. I'd say, okay, well, I got to test 1.07 times 5.6. Then I would test 1.111 times 5.6, and I would test 1.125 times 5.6. And whichever one of these options spits out 6.3, that must be the correct option choice. Now, if you're confused why I have where I'm getting this 1.07 from or this 1.111 from, all I'm doing is I'm combining two steps in one go. Like, for example, let's do this. So if I was doing the 7% thing, that's really just 1 plus, and then if I were to write 7% as a decimal, that's 0.07. So I'm just kind of saying, recognizing that 1 plus 0.07 is just 1.07, for example. That is the plug and chug method. Honestly, that's the fastest way to do this problem. So that's kind of sad that the SAT math test comes down to that. But anyway, if you wanted to do like traditional pen and paper, no calculator section type problem, you could just solve for this like this. And it's good to see 1 plus x over 100, because again, percent is just per 100, times 5.6 is equal to 6.3. And then you could isolate by dividing both sides by the 5.6. And then you would subtract the 1 from both sides. And then you'd multiply everything through by 100. And then you'd be left with the x, which would be your percent number. So that's how we could handle this problem. Let's look for, oh, lovely. Look at this. We have a greater than problem. We have this, what number is 20% greater than 60? Okay, so whenever you see this what number language, that just means you're gonna have a variable. So let's call that what number x. This is x. So what number x, this number x is means equals. So what number is 20% greater than 60? Okay, so how do we handle this greater than 60? Well, that means I start with my 100% or just one. And since it's greater, I need to add that 20%. So I'm adding 20%. I'm just doing that as a decimal of 60. So this 1.2 times 60 is precisely the number that is going to be 20% greater than 60. Okay, so that's how you'd set that up. Actually, now that I'm looking at, I actually really like question 4 here because this is, it would be one of those types of questions that looks really tricky just by the way it's worded, but when you really break down what it's saying, it's not that bad. So for example, the number y is, so again, we got to practice putting these things into equations. The number y is 20% greater than. Okay, so whenever we have this greater than language, it's the same thing as kind of increased by. So 1 plus how much am I greater than? I'm greater by 20%. So I'll put that as a decimal. And I'm greater than this number x. So fantastic. I already have an expression for y. Y is 1.2 times x. And then let's read the next clue here. Z is 20% less than y. Okay, so we have another comparison. So z is less than, okay. Well, I start with the original amount, but instead of being greater, I'm less. So I need to subtract that percentage value. Of what? Of y. So great, I have an expression for z. Z is, whoops, z is 0.8 of y. So then now we're asked to compare the number z is how many times x, or basically just need to get z and x in the same equation. And we can do that through the shared variable y. And so then we just need to do a little bit of algebra to isolate for y. So y in this case is 0 z over 0.8, right? If I isolate. And so now I set this equal to this. So 1.2x is equal to y. And guess what? Y is also equal to z over 0.8. Now, the question specifically only wants the z is how many times x. So I want to isolate z. So I'll just kick over the 0.8. So z ends up just being whatever 1.2 times 0.8 times x. So obviously the number they're after in this question is this product between 1.2 and 0.8. And then you'd have your answer. I'm trying to find a Oh, I like this question. Just because as an example, it shows that percentages can be greater than 100%. That's totally fine. The concept doesn't change. This is a example of X% of Y. And so all I'm doing is I'm converting this into a decimal. So 1.2 of means times and 2000. Boom, one step, you're done. Okay. So some of these questions are really straightforward. Let's see. Again, this is a great example of just this increased by. So this is an example of variable increased by some percent. Okay. So what we're doing, increased by that percent means that I have 1 plus 5%, 0.05, okay, times my R, which is just 1.05 R. Bingo. So we're already done. So once you get used to the language and converting it into these expressions, these are all going to be really really nice. Let's see. Oh, I really like 11 because this gives us a way to practice this decreased by p%. Okay, so a car was listed with a price of this much. Okay, fantastic. So they're telling us what we're starting with, and then it decreased by a certain amount of percent. Okay. And once it decreases, then we're told that the end result of this should end up being 9,600. Okay. So I'm starting with $12,000 and I'm decreasing it. Okay. So what do I know about decreasing a number by a certain percentage? Well, take 100% of it and I subtract that p%, which in this case, let's represent this as a fraction because we have that variable. So p%, p per 100. Okay, well, what am I decreasing? I'm decreasing the original price. So I'm decreasing my original price of $12,000. And what happens after I make this decrease? Well, I spit out this new decreased value of 9,600. Instantly, you can see this is just a linear equation and we're solving for P. So that's kind of the strategy you want to take for these percentage problems. And then I think we will let's do two more examples because I want to do 12. I like this. It gives a 20% discount. Okay, so notice how discount isn't necessarily the English word decreased, but we all live in a society. We know that discount means it's a percent decrease. So if a teacher is paying this much, they're paying 14 bucks for their meal after, okay, that's key, after the discount was applied. So basically what that's telling us in the practical sense is that this value of 14 is kind of acting like how this value of 9,600 up here was like, this is the price after you've decreased it. What was the price of the meal before we applied the discount? So how much was originally charged? And then that original amount was decreased by 20%. And then now the end result of that is this 14 bucks. So although that isn't necessarily written out and spelled out in plain words, that is what is going on. And then we can make our expressions based off of that. So let's just call the original price of the meal X because we need some sort of a variable. So let's call it X. And I know that if I take a 20% decrease of it, so I'll take my 100% or 1, and I am decreasing because it's a discount of 20% of the price of the meal. Okay, so I've decreased it by um this amount. I know that that should spit out the value 14. In other words, I have 0.8 of x is equal to 14, and just like that, with one computation, we will have our answer. Okay, so that's an excellent example of a more practical example that doesn't use the words decreased by or increased by, but it's heavily implied by just how we know the world works and how these problems work. And then let's see. I know I didn't really talk about this on the whiteboard, but these exponentials, right? So if you do a percent over and over and over and over again, you're basically multiplying by something over and over and over again, which is pretty much what we mean by an exponent. Okay, so for example, question 14, each year the value of an investment is increasing. Okay, fantastic. So if it's increasing automatically, that's signaling to me that we're going to have something greater than 100%. Specifically, it's going to be 1 plus this 2.5%. And so that's what 2.5% looks like. So I'm anticipating seeing a 1.025 somewhere. So straight off the bat, I'm looking for this number. Funnily enough, that kind of actually answers the question because that's wrong, and that's wrong. But in case the option choices weren't so clear, we can take a look at the rest of this. The initial value was $500. Okay. Whenever you see an initial value, that is signaling to you this is the number that doesn't have the exponent on it. It's this constant number that's standing out front of the actual exponent that's going on. And so naturally then, here's my increasing percentage every year and an initial amount. Okay. So that's pretty good. I think I'll end it there. Obviously, if you have questions about problems and things, continue to ask them. But yes, really, really try to practice converting these percentage questions using this very straightforward um, understanding of the expressions. Because if you can do that, almost every percent question turns into a linear equation or something like that. And then those are much easier to solve than trying to intuitively guess what they mean by the percents. Okay.